It's my great pleasure to be here. I imagine some of you have heard me talk about the asteroid impact hazard before. It's been almost 20 years since I gave the first talk on that subject on Capitol Hill to staffers from the House of Representatives. And for at least the first 10 of those 20 years, I was generally known as Dr. Doom, because I was pointing out that there is a hazard from asteroids, that asteroid impacts, that it's roughly comparable in quantitative terms to the risk we all run from other natural hazards like earthquakes and volcanoes. And so it's something we should do something about. And for all those early talks, I always said, but we aren't doing anything about it. And I'm often quoted as having noted that the total number of people on planet Earth that are involved in protecting us against asteroids was about equivalent to one shift at a McDonald's restaurant. Well, I'm here to say that we are doing something about it. And so for the last few years, I've tried to erase the Dr. Doom hat entirely and talk about the progress we're making and the next steps we need to do. Much of the progress to date, in fact, almost all of it, has concerned asteroid surveys. You probably are familiar a little bit with the so-called Spacegaurd Survey. Was first recommended at congressional request by a committee I chaired for NASA in 1991. In 1998, as the technology kept improving and our ability to detect asteroids, Carl Pilcher, who's sitting here, who was then speaking officially for what was then space science at NASA, told the Congress that NASA would carry out the Spacegaurd Survey with the goal of finding 90% of the near-Earth asteroids larger than 1 kilometer within 10 years, which means right now, a week ago. And that has been carrying along with great success, finding the majority of the large near-Earth asteroids. What you do is search with a telescope in an entirely automated fashion. This is not something people can do, so it depends completely on modern computers and CCD chips. You image a part of the sky, you go back 20 or 30 minutes later, do it again, then do it a third time, let the computer take the differences and get rid of all the hundreds of thousands or millions of fixed stars and find the small number of faint moving points of light. This is a process that is mostly done by 4 telescopes and a few others contributing as well. The data are processed very quickly. They're normally posted on the web by the afternoon of the following day from when they were taken. Orbits are calculated, again in a fairly automatic fashion at both the NASA NEA Program Office at JPL and at a similar technical facility at the University of Pisa. Both of those run websites and put it up. If you ever find yourself completely bored, or if you're a journalist and it's a slow news day, you can probably go to those websites and see exactly which asteroids are going to come close to Earth, which ones have a non-zero chance of hitting us, and so forth. There are a number out there, including Apophis, the asteroid I'm going to be talking about today, that do have a non-zero chance of hitting the Earth. But it would not be fair to say there's a prediction that anything will hit. In fact, the probabilities are pretty low. When I talk about the probability of hitting Earth, I'm not referring to some sort of stochastic random thing. The fact is, the asteroid knows for sure whether it's going to hit the Earth or not. Newtonian mechanics works. It's a deterministic problem, at least on the time scale of a century or two. The thing is, we don't necessarily know because our observations are imperfect, and so there's a certain uncertainty associated with defining the orbit and projecting it forward in time to see when the asteroid might intersect with the Earth's orbit at the same time and we have a collision. One of the first accomplishments of the Spacegaurd Survey was to recognize that there are no near-Earth asteroids as large as the KT mass extinction object out there now. We can't say anything about comets that come from the Oort cloud from deep space, but as far as asteroids are concerned, we are not about to go the way of the dinosaurs. And this may make you feel good. In the 80% of the asteroids, not 90 I'm afraid, but the 80% of the asteroids larger than 1 kilometer in diameter that have been tracked, it also appears that there's nothing going to hit the Earth in the next century or so, which is how long you can project orbits with some accuracy. I will make a provocative statement, and you can argue with me afterwards. I would say, therefore, since the bulk of the risk, the a priori risk, is due to asteroids in this 1 to 3 kilometer size, that we have removed 80% of the chance of your dying from a near-Earth asteroid collision. You can argue with me afterwards. This is an arguable point, but one thing to say is that we have actually retired 80% of the risk. That's the good news. But now we change perspective and think about the smaller asteroids. Asteroids follow a power law size distribution. There are vastly more small ones than large ones. While there are only about 1,000 near-Earth asteroids larger than 1 kilometer, there are something like 1 million larger than 100 meters. And at least that many, therefore, that are larger than the Tunguska blast, which took place a century ago in Siberia, with the energy equivalent to a 15 megaton bomb. A city killer, something that could, if it hit a city, destroy it. The probabilities of this happening in any 1 year are still pretty small. And of course, the probability that you will be sitting in that city or in that impact point is much smaller yet. So the actual hazard that each of us experiences, that we will die from an asteroid impact, is mostly from the 1 kilometer and larger. Nevertheless, one needs to consider the smaller ones, and it's a simple fact that the next asteroid that hits the Earth and causes an explosion, something more than just a meteor, is likely to be in this 100 or 200 meter size range because there are so many more of them. And we have so far found fewer than 5% of those. Thus, we are beginning to focus our minds on where the next step in the problem would be. First, are we going to carry out a survey that will extend the size limit down from 1 kilometer to perhaps 200 meters? It's going to take a lot bigger telescopes, and it's going to cost a lot more. And so you have this interesting thing that the less expensive part, which we've already done, has eliminated the larger part of the risk. But we now face the policy question of whether to spend more money to deal with the more frequent but actually less hazardous impacts. How you feel about this depends on whether you're a scientist. Naturally, scientists always want to find out more things, discover more objects, improve our statistics. Or a politician. One leading politician involved in actually promoting asteroid surveys from the southern part of this state has said categorically that as far as he is concerned, it is unacceptable that an impact could occur at any time and kill 1 million of his constituents without warning. Unacceptable. No probabilities, no calculations, no orbital statistics. It's unacceptable. Well, that's an extreme on one side. I mean, clearly you don't spend infinite amounts of money to deal with very small risks. But somewhere in between lies the reality that if we do fund the next generation of surveys, then it's probable that we will actually find the next asteroid before it hits us. And it's probable that that one that we find will be in the couple of 100 meter size range. Therefore, capable of producing an explosion of hundreds of megatons, which would be very, very bad near ground zero, but would not have a global effect. So we're talking about protecting against, first discovering and then ultimately protecting against the more local risks that nevertheless are the most likely and the ones we're most likely to deal with. Now, until now, we've had to say that since we have found only a small percentage of those, we basically can't make a prediction. And I want to emphasize that we're now not talking about the scientific problem that you can deal with by statistics. Some people have said, well, we just need to have a better estimate of the probability of an impact. That's what scientists do. Public policy people don't want to know the probability. They want to know when and where it will actually happen. And the analogy I often give is if you walk out across a busy street, like Central Expressway, and you're standing on the corner and you're deciding whether to step off the curb, do you ask yourself what the statistical probability is that you will be run over by a car? Or do you look and see if one is coming? And that's exactly what we want to do with more advanced surveys. What we've done so far with the Spacegaurd Survey is to try to actually find them one at a time, not to improve our statistics, but to locate any that are actually dangerous. I think these surveys will take place. Right now, we have to say the most likely warning that we will have of the next impact is about 4 seconds. You won't know about it until the sky lights up as it enters the atmosphere. Don't anybody think that there are a whole bunch of folks out there, with binoculars scanning the sky looking for incoming objects. The whole idea of these surveys is to find them decades in advance and predict. You find them not on their final approach to Earth, but on some previous, because they will go by thousands of time before the orbits line up right for an impact. But the chances are pretty good in the next 10 or 20 years that we will be finding a lot more objects, tens, hundreds of thousands, that several of those will be potentially threatening. And somewhere along here, we're going to find one that is going to hit the Earth, probably with decades of warning. Then what do we do? Is this an international problem or a national problem? Is it something decided by scientists or politicians? There are lots of interesting policy questions, but I'm going to skip over that now and talk instead about the specific desire to get more concrete information on what these objects are like, partly because it's scientifically interesting. Lou, why don't you sit on the front row? You can have my seat. Lou Friedman from the Planetary Society. You all know him. Where was I? What information would we like to have about the small near-Earth asteroids, both for scientific potential, but much more specifically if we need to protect against one? In one sense, of course, you can't really predict because every asteroid is different. And when you actually finally find the asteroid that is at least a potential threat, you're going to have to focus on that object to see what you can do about it. But before that, I contend that there's a great value in looking at a small sample of the near-Earth asteroids to begin to understand what it would take to protect against them, and incidentally get some good science. By protect against them, of course, the simplest thing is evacuate where it's going to hit. And for that, all you need is an orbit, but it has to be an extremely precise orbit. It's an issue now not of whether it will hit or whether it will hit in this hemisphere, but locating the actual point. Maybe if you knew within 100 miles where it was going to come down, you could evacuate or do something. Other than that, the prediction isn't worth much, and so it would have to be a very precisely understood orbit. Finding orbits is one important thing. The other, of course, is could we use space technology to deflect it, to change its orbit so that instead of hitting the Earth, it misses. And the problem, in a sense, is very simple. If here's an asteroid and here's the Earth, and they're both going around, and sometime, say 50 years from now, they're going to intersect and hit. The Earth crosses its own diameter in about 6 minutes along its orbit. So all you have to do is delay the asteroid's arrival by 4 minutes, or speed it up by 4 minutes, and it'll miss. So what you need to do is change the orbital period of the asteroid by a very small amount. And of course, the longer you know in advance, the simpler it is, the less momentum change or energy you have to apply to change its orbit. How do you change an asteroid's orbit? Well, I'm not going to go into detail, but I think it's fair to say that most technologies by which you might change an asteroid orbit depend somewhat on the nature of the asteroid itself. What's its shape, its density, how's it spinning, what would be the response if you hit it with a nuclear explosive or if you rammed a spacecraft into it. So the subject for the next 20, 25 minutes here is going to be missions, low-cost missions, that could go to one or more small near-Earth asteroid and obtain the information we need about their orbits and their physical properties. One such mission has already been flown, the Japanese Hayabusa mission to asteroid Itokawa. Not entirely successful in their own terms, but it gave us a whole look, and Itokawa doesn't look anything like the larger asteroids. It's clearly a different kind of object. In fact, many of these are going to be monoliths, unlike the bigger ones, which are often gravel piles, because they basically lost their pieces in a series of previous impacts, but not necessarily. Some of them could be just loose conglomerations. The surface gravity is extremely low on these objects. On any asteroid, any near-Earth asteroid, you could jump off and launch yourself into space. These little guys have so little gravity that if you so much as move an arm on a spacecraft, you might launch it into space. The whole concept of landing the way we normally think of with targets in the solar system doesn't work. Docking is the term that the astronauts prefer for what you would do with such a small object. But we need to understand some of them, and our minds are focused now on asteroid Apophis. Have you heard of Apophis? I expect everybody has. Apophis is an asteroid which illustrates a lot of peculiarities of asteroid orbits. When it was first found, for a little while, for a day or two, we actually thought it had a better than 1% chance of hitting the Earth based on preliminary orbits. But the orbits improved, and we found that it will not hit the Earth on its close pass on Friday, the 13th of April, 2029. It will, however, come only about 10,000 kilometers above the surface of the Earth. It'll be inside the orbiting geosynchronous satellites. It'll be easily visible to the naked eye. It'll be a fascinating object for scientific discussion. And because it will come so close, actually, if it's not a monolith, it's likely to start shifting things around under the tidal effect of the Earth. So a very interesting opportunity, but that's not all that makes it interesting. The fact is that when it goes by Earth that close, its orbit is torqued around, it is bent, and its orbital period is changed. One possibility, when it comes out of this encounter, is it will be on an orbit with a 7 to 6 resonance with the Earth, and will come back on April 13th of 2036 and hit us. And whether that happens depends very exquisitely on how it passes Earth the first time. The question is phrased in terms of, can it pass through a keyhole, which is a dynamical fiction, really, but a dynamical spot on the Earth trajectory intercept, where if it goes right there, within a kilometer, it'll come back. If it goes through any other point, it won't. And so there's an obvious interest in knowing whether it will go through a keyhole. That's one thing you would like to do. I mentioned Lou Friedman on the Planetary Society because they've had a lot of interest and an actual competition to design a mission that could tag Apophis, that is, could go there and determine the orbit with sufficient precision to know whether or not it will go through the keyhole. And that's part of what I'm talking about with our mission.
What is the cross-section of the keyhole compared to the size?
It's about 600 meters across. And the uncertainty is 1,000 kilometers, perhaps. Yeah, of course, as the uncertainty shrinks, you don't know whether the probability of going through the impact will go higher or lower. You know, you can't predict it. Let me say right now, philosophically, that almost all of this discussion of asteroids is predicated on the fact that the highly improbable could happen. If you wanted to just play the odds, of course, nothing's going to hit the Earth in our lifetimes. Any new object discovered, I've had colleagues get up and say, well, you know, it looks like it might hit the Earth now, but we are sure when more data come in and refine the orbit that it will miss. And they're pretty safe to say that. But we're only in this game for the exceptions. I mean, the interest is the odd one that won't conform to our expectation. If you just wanted to play the odds and be a media hero, you could immediately claim, as every new asteroid is found, that one will not hit the Earth. I am sure that as more data come in, will turn out to be safe. But I, perhaps through a certain degree of perversity, look at the other side. Well, what if? So, the name I should mention, asteroids with orbits inside the orbit of the Earth, less than 1 year period, are called Atens and are named after Egyptian gods. Those outside are called Apollos and are named after Greek gods. Apophis actually changes from one to the other as it goes by the Earth. I think it's now an Aten and it ends up an Apollo. And Apophis is an interesting name. It is the Greek name for the Egyptian god of chaos and destruction. And the mission I'm going to tell you about that we've been working on at NASA Ames is called MOT. It's kind of a bad acronym, but it's an interesting choice because MOT is the Egyptian goddess of peace and stability. So maybe if we fly MOT to Apophis, we can end up moving it from the category of dangerous and chaotic to peaceful and benign. So I'm going to go through quickly part of a presentation. See what it takes to get this up here. What is there? Good. That we made to NASA headquarters a month or two ago. It's a bit awkward. You will see a lot of these charts have notes saying, you know, proprietary or pre-decisional. And I think I've removed anything that actually is proprietary. But you're seeing a fairly raw presentation of a mission study that was given to NASA headquarters. It's certainly not the only way to go to Apophis, but we have really tried to reduce the costs so that we can get just the data we need. No more, no less. Pardon?
Proprietary for whom? NASA or some company or what?
It's a little bit of all. You know, there are 3 or 4 NASA centers involved. There are a couple of industries. Don't worry about it. I don't think I'm going to show you anything that you should worry about. I'm just telling you, you'll find this word at the bottom of some of the charts. Right. And it doesn't worry me, and so therefore we're all okay. So this is a study we carried out, and I'm just starting to say what's awkward about is that there is no obvious mechanism in the NASA Science Mission Directorate to fund planetary missions in the $100 to $200 million price category. Because the smallest one they have is Discovery, which is up to like $500 million. So we're not quite sure what slot we would compete in with a mission that's this cheap. It's not so cheap that you can do it out of pocket change, but it's not as expensive as the normal competitions. But let's put the politics aside and just look at what this might be technically. This gives you the very high-level overview. It's a low-cost rendezvous mission to Apophis. It's designed to do both science and tech demonstrations. By science, I mean not only to understand it, both from a scientific perspective and from whatever the information that gives you about possible future deflection. And a lot of the payload is derived from the instruments on the L-Cross mission, which is being developed at Ames that you all know about. So we were able to get things a lot less expensive and already developed. And what thrills me about it actually is how simple some of this is. I have had the experience of going to JPL, just to name one random center, and see about the availability of instruments that they've used on planetary spacecraft. So the typical instrument weighs 10 kilograms and is this big. We're talking about instruments here that are considerably smaller than a Coke can and weigh half a kilogram. And if one can do that, of course, the whole mission scales down and is easier to do. So let me go through this. We'll come back to that. That's a tech demo that is not needed for this mission. But frankly, we're trying to pull together a series of constituents that would find it useful because laser communication has not been demonstrated and is potentially very good for planetary missions. The argument, as I said, is that the information we get would be useful for both science. The Science Mission Directorate is the one we're pitching this to, and for planetary defense. That the small ones are the most likely to hit the Earth, and Apophis is the best known small asteroid. Also, incidentally, Congress specifically asked NASA to study low-cost mission to Apophis. And that's quite unusual, and I don't understand all the politics of how that got in there, but it's there, and so that raises this to a certain level of interest. The argument is that both the science and defense requires pretty much the same information. You have to know its size, shape, and spin vector, and orbit, of course. It's very important to get some idea of its internal structure, what it's made of, whether it's a monolith or a rubble pile, because in many of the deflection scenarios, whether you hit it with a ballistic impact or a small nuke or whatever, its response depends very critically on whether it's soft and squishy or hard, whether things will spall off the surface or not. In fact, if you consider the simple kind of deflection in which you simply impact ballistically with a rocket like we did with Temple 1 with deep impact, the actual change of momentum of the object can vary by as much as a factor of 10, depending on how it reacts, whether you excavate a big hole and blow things out, or it just gets absorbed like throwing a baseball into a snowdrift. And so the actual efficacy of a defense system depends a lot on knowing something about the interior. But to land and drill and do seismic experiments is very expensive. So part of what we try to do here is get a compromise. Can you find out enough about the structure without a high-priced mission? Another issue is the Yarkovsky effect, which some of you I know are familiar with. It's a very cool thing, really, because it says that if you can have a continuous thrust, even though it's extremely small, that you will eventually change orbits of asteroids, and also their spin, by the way. And that continuous thrust is provided by the fact that sunlight is absorbed on the sun-facing side, but the infrared radiation comes primarily at an angle from that because the asteroid is spinning and its hottest part is offset. And believe it or not, that tiny momentum change of that infrared radiation asymmetry is able to change an asteroid. And we're just to the point where we can both measure the infrared radiation from the asteroid and measure the Yarkovsky effect by tracking it for a few years. And it's been actually measured on a couple of asteroids so far. So this is just a chart showing you where we stand on the surveys. 5,000 or so near-Earth asteroids known, 1 million out there that could be found in the next few years. Somewhere in there is something that probably has our name on it. Now, how can we learn what we need to know about these small asteroids? And let me start with the note at the bottom because it startled me a little bit, and I just want to say it over and over. Eros is the one near-Earth asteroid that's been studied in detail with the near Shoemaker mission that orbited and landed. Eros is 1,000,000 times smaller than the moon, but it's 1,000,000 times larger than Apophis. Apophis is to Eros as Eros is to the moon. So what we learned and the spacecraft techniques we used for Eros are not going to apply to Apophis. And that's why we have to think, or any sub-kilometer asteroid, we have to think in terms of this. So we start with what can you do from the ground? Well, you get a brightness. You measure the brightness as a function of time. You probably get a light curve which can give you, perhaps with a factor of 2 ambiguity, the spin rate. And in some cases, though very difficult with a small object, some idea of the spin vector. What you can learn about the shape is from the amplitude of the light curve. But that, again, depends on the spin vector and the orientation. You can tell if it's twice as long as it is wide from the amplitude. Measure ratio of the major axes. If it's bright enough, and not many of these little sub-kilometer asteroids are, you can get a good spectrum in the visible and infrared, get something about the mineralogy of the surface, perhaps connect it with the known asteroid classes and the known meteorite classes. That's about all. Ground-based radar is, of course, wonderfully capable if the object comes close enough. The Goldstone and Arecibo radars will give you an image of it, perhaps with 100-meter resolution or 50-meter resolution. Much better spin vector and shape. By the reflectivity, you can probably tell a stony object from a metallic object. And of the greatest power, in many ways, of the radar comes when the object is, if it's part of a binary pair or has a satellite, because then you can measure density. Mass and density. And a surprising number, almost 25% of the NEAs that have been looked at with radar have had a companion. But not the little ones. A sub-kilometer object the size of Apophis or Itokawa that can't have a stable satellite orbit. And so that doesn't work. We're going to have to go there to find out things like mass and density. Yes?
Why are you saying you can't have a satellite orbit?
I don't think there's any satellite orbit that's stable for long periods of time for something as small as Apophis. If I'm wrong, correct me.
I think the problem is if you have a spacecraft there, you have a lot of trouble. Because the spacecraft is perturbed by gravitational forces of the sun, by non-gravitational forces. That's significant. You don't have a stable spacecraft orbit.
Because the spacecraft's lower density, in effect?
Because the spacecraft is lower column density. Much lower column density, even than a 10-meter size satellite.
Jack Lissar knows dynamics as well as anyone, so I'll take your correction. I'm not sure I believe it, but for now, let's accept it. Anyway, we haven't. The other problem with radar is that the little objects really have to get awfully close before you can study them.
And just the tides will also have an effect on the stability of any of the asteroid. And that's also one reason for which we did not observe yet satellites around sub-kilometer NEAs. Maybe there is some, but an NEAs which has close encounter with a terrestrial planet, we lose its
Right. You can strip off moons pretty easily. Then there is the fact, and I regret to say that there was a major NASA study that recommended this as the way to study small asteroids, is with flyby missions. Now, flyby missions are wonderful. Think of all that Voyager accomplished with flyby missions. Think of what include the several missions that have flown past big main belt asteroids, like Gaspra and Ida. And in some cases determined a mass and certainly got a lot of valuable data. But we're talking about an object that's 1,000,000 times smaller in mass. If the asteroid is 1 kilometer across and the spacecraft passes it at a typical flyby speed of 5 kilometers a second, my simple arithmetic says it goes by in 1/5 of a second. Maybe you get a couple of pictures as you sweep past. You get no mass because there's no measurable deflection of the orbit. You don't get a shape. You don't get a spin vector. it's almost useless. And I think it's silly to think about a flyby mission. If all you wanted was PR, then yes, you could fly by 5 asteroids and get one picture of each one, and it would be above the fold on the New York Times, perhaps. But I don't think it would solve the problems that we need to solve.
Okay.
Yes?
At what point will we be able to not have to spend money, significant money for a flyby mission, but just know enough of these that when we go into Mars or whatever, we'll have one with a trivial delta V, be able to take snapshots, get those low quality, but better than from the ground data?
I don't know. It's a good question. But of course, I would say that we already have some of those lower quality data from the radar. I mean, there are radar images, low resolution radar images of sub-kilometer asteroids. Of course, the chances that you will get that opportunity with one of particular interest like Apophis become vanishingly small. Whether you really think Apophis is enough of a danger to be worried about, I don't know. But that's kind of the politically correct thing to say now. If you're going to go to any sub-kilometer asteroid, it should be Apophis. Well, let me go on and talk about this mission. Jack was part of a study with me in which we looked at a lander. This mission I'm going to talk to you and advocate for is a rendezvous. It flies in formation with the object, so it can get close enough and stay long enough to determine mass and get beautiful, complete imaging as it rotates, get the size, get the shape, get the surface slopes, all of that information, and of course determine a very good density, which is the first clue you have to interior structure. So the argument here is that the best compromise between high quality and low cost is a simple rendezvous instrument, which can actually carry very few instruments because much of what you do is tracking the spacecraft and using a LiDAR to measure the distance from the spacecraft to the surface and good imaging. And there are some other nice things like infrared, but basically with just good tracking and good imaging and good ranging, you can find out a lot about it. Again, I point out you can't go into orbit around it. You don't try to go into orbit. You fly in formation, and it takes only very small adjustments in the spacecraft trajectory corrections to stay with it. In fact, the way you do a mass, since you can't go into orbit, is you start out and you aim to fly by a kilometer or two above the surface. You turn off everything. You stop using your thrusters, and you just drift over a period of, say, a week or 10 days past the object, measuring exactly how much change that produces in the spacecraft orbit. You track the spacecraft, and in effect, if you know where the spacecraft is relative to the asteroid and you're tracking the spacecraft, you can get an extremely precise orbit for the asteroid. Maybe not good enough to tell whether it will go through the keyhole, but certainly pretty good. And you don't have to land. That's my point, that you can do this. In fact, you can do it much more easily with the rendezvous spacecraft. Because once you land, think of all the problems that hit you, other than just the technology of landing and staying there. You're on a rotating object. The sun is rising and setting. You have thermal stresses and daily diurnal variations. You have to build a whole thermal system to deal with that. You have to build a power system that deals with it if you're based on solar cells. You have to build a communication system that can either track the Earth or track a mother spacecraft or turn it on and off in bursts. Everything. It doubles, triples the cost of what you're doing relative to a spacecraft that is free-flying, that can always orient itself with respect to the sun and the Earth, and doesn't require dealing with these variable things you run into on the surface. So the mission's goals, and this includes both the science I'm talking about and the technology that can be demonstrated. Determine the baseline orbit with better precision than from the ground, including ground-based radar. Characterize the mass, shape, density, spin vector, global surface imaging, slopes, all that information that you can try to use to find out what kind of an object it is. Then, programmatically, if you can demonstrate the low-cost mission, maybe if you could do that, you could go build 2 or 3 of these and go to different asteroids for the cost of one normal mission. And then I'll mention this at the end. There's a particular approach using as it's launching as a secondary payload. And also, there are folks who would like to fly a laser communication system on it. Not that we would actually use it, but just piggyback along. And of course, if they'll pay part of the cost for that opportunity to take a ride, that might be just what it takes to enable the mission. The launch opportunities for Apophis come up in about 2012, 2013, the good ones. One problem with an asteroid that comes very close to the Earth, if it has a roughly Earth-like orbit, is that the synodic period is very long. That is, its period around the sun is nearly the same as the Earth. It comes close, and how long does it take before it comes close again? In this case, 5 or 6 years. So your launch opportunities are quantized that way. So if you want to do it soon, you need to do it in about 2012, plus or minus a year. And that means you'd have to get started on this mission very quickly. If you can't make that, then push reset and slip 6 years, or find out, or use a bigger rocket, or whatever it might take. But this looks for a 29-month development, launch in February 2012, 3 months for physical characterization, 6 more months of tracking the spacecraft to get the improved orbit.
How long a trip?
About a year. And I'll come to that because there are several launch options. If you fly on a direct trajectory from Earth, and which means you have to pay for the rocket, then you can get there in a little less than a year. If you launch on a secondary payload, which is a lot cheaper potentially, then you're just piggybacking on somebody else. And that somebody else simply lobs you out into Earth-Moon space. And then you will spend months maneuvering with lunar flybys and Earth flybys to reorient the orbit to finally get the trajectory to the object. So you have to launch 6 months earlier or a year earlier and go through this maneuvering if you can't launch on the direct vector to the asteroid. So this is all a trade of cost versus time. You will recognize some of these folks from the science team that were involved in this study. The instruments, as I said, have a heritage primarily from L-Cross. And I wish I could get Tony to let me bring one and show you, because they're just little things you hold in your hand. I said the size of a Coke can. The mapping camera is closer to the size of the roll inside of toilet paper. And these things exist. They've been checked out. They're going to be launched to the moon in April. Whether that means they're proven or not is something you can debate, but it seems like this should be possible. And goodness, if you just go down to Best Buy or Fry's and look at the capability of cameras, for instance, that are weigh 3 ounces, it does seem like you ought to be able to do that on a space mission as well. The nominal thing is a navigation camera, because you can't track this thing from Earth very well. You have to ultimately find the asteroid with the spacecraft's own camera and use that to come up close, because you're not tracking it from Earth. The asteroid can't be seen from Earth except when it's relatively close. Then a mapping camera, a mid-infrared camera, the laser ranger, to measure the distance between the asteroid surface and the spacecraft. And that's really all it is. And if you look at the mass on these, you see the navigation camera has that big lens on it. Mapping cameras weigh 300 grams, and you can put 2 or 3 on. The laser ranger is the biggest at almost 4 kilograms. Think about getting in there and what we normally talk about of resolution with an asteroid like Apophis that's only 300 meters long. If you think of the old standard format Voyager pictures that are 1,000 pixels across, and you do a 1,000 pixel across picture of the asteroid, you're already getting 30 centimeter resolution. As you get closer, it gets even better. But my point is, you don't have to take just a whole lot of pictures to cover the entire surface at, say, 10 centimeter resolution. You do have to maneuver into different lighting angles and different positions. And this just shows examples. If you were a range of 2 kilometers, what kind of field of view you would get with these cameras. But the bottom line really is, 100 really good pictures is enough, plus the laser ranging, to find out a whole lot about it. I mentioned this plan before, 3 months for physical characterization and 6 months for orbital characterization, and then the issue of just talking with Lou and others about how you get there. These are the science products you would get. You get the orbital trajectory. This says always the word model is added. What you're determining is a model in all cases. You use the imagery and the laser ranging to get a very precise shape and rotation, and you plot surface angles and all these things that one does. You get a mass to within a few percent by doing several of these slow flybys. And then there's a certain magic that I'm told by people who are expert at this, that just by putting it after a year, putting all the data together from all the tracking, you can keep improving it. We have looked at a variety of mission designs. There are always an infinite number of possibilities. The one that we have talked about, that we mostly tried to advocate for, was the one that launched as a secondary payload. And that's with a system called the ESPA ring, which is simply the connector between the spacecraft and the main satellite. So you have something this big around, this high, and you build the spacecraft and the rocket engine into that intermediate stage. And so somewhere during the launch on the way to high orbit, you release this from the main payload, and it's real funny looking and real ugly, and it doesn't look like a rocket at all, but it is. And so here's the spacecraft hanging out on one side, a tank, a rocket there, and use that to get your primary delta V plus these multiple flybys of Earth and Moon to get you to the object. And slow down when you get there, because it's a rendezvous. You have to match orbits. It's not just get there as quickly as you can. Now, the beauty of this is twofold. First, the launches are free if you can go along with somebody else. Secondly, it can develop a capability that doesn't now exist for sending other payloads with this kind of simple rocket built into the connector between the upper stage and the main payload. The disadvantages are that you're dependent on somebody else's launch, that you don't end up on the right trajectory, and that therefore you have to launch 6 months or a year earlier. So if time is of the essence, you do much better to take the time and launch on a dedicated launch vehicle. That is a political, economic issue that I don't want to argue here. It doesn't matter to us which way we go. There's even a third possibility. You put a solar electric propulsion on. That reduces the mass, reduces the requirements, but takes longer. Is that a good trade? Is it a good trade to save mass now, but spend an extra 2 years getting there? Well, perhaps not. But these are all trades that could be done, and the spacecraft itself is pretty much independent of the mode you have for getting there. This is a spacecraft that Ames has been working on for some time in different models, including this ESPA ring configuration. So my conclusions, and I hope to quit now because we want to have a discussion, is that we think a rendezvous spacecraft with a simple spacecraft is the best way to find out what we need to know about a near-Earth asteroid, recognizing that they're very small, have very low surface gravity. You have to get close in and stay there a long time to get the data you want. Now, as part of selling it, there's the possibility, as I said, of using this as a demonstration for the deep space laser communication. We could even use it, I suppose, but we're not depending on it. In fact, we might even just kick it off before we got to the asteroid and simply use the year going to the asteroid to test it. And you do that if they want to pay for it and you have the mass margin. We would like to get funding for this, and so you'll probably ask how much it costs. The core spacecraft and mission is under $150 million. Whether the whole cost is that depends on how you allocate these other things. The launch vehicle, whether the Air Force will help us build the ESPA ring, whether MIT will provide the communications, and so forth. Could even almost come down to $100 million, but I think that's unrealistic. Certainly less than $200 million. And again, this becomes a political, technical jockeying. But I think if we want to understand Apophis, and we want to understand other near-Earth asteroids, and we want the information to begin technical planning for how you would deflect an object if it actually threatened the Earth, that this is a very good approach for doing that. Thank you.
Thank you very much, David. We have time for some questions, and I'll remind everyone this microphone doesn't magnify your voice, but it does get your question recorded for our future web presentation of the lecture. So questions?
Just naively, one would think that just trying to figure out how such an object would react to an impact might be one of the larger issues if you're interested in the topic you're talking about. It doesn't seem that your particular proposal here addresses that aspect.
Only in the sense of trying to find out if it's a monolith or a rubble pile, but there is an orthogonal and complementary approach that's been thought about a lot. When you have a spacecraft there, our spacecraft or any other in formation, then with a completely separate launch on a completely separate kind of trajectory, you run something into it. JPL has sometimes said, you go to an asteroid or comet and we'll bomb it. And that way, unlike Deep Impact, which had a terrible time getting really any information and we couldn't tell how much the orbit of the comet was changed by the impact, that way, observing it before, during, and after, you have an extremely powerful thing. And this, of course, is an option for international cooperation, too, because the two spacecraft never touch. They aren't launched together. They could be done in completely independent ways, and yet the results are highly complementary.
Could you just repeat how long it will be rendezvousing with the asteroid?
The nominal is 9 months, 3 months in which it maneuvers around for the physical characterization, and then another 6 months of tracking.
And at the end of it, what happens to the
Throw it away.
Okay.
You don't want to hit it. Landing on the surface might be fun, but when you're dealing with something that actually has a finite chance of hitting the Earth, I think hands-off is the best approach. I would hate to be in that position. You know, if you touch it, you own it.
That was my question precisely. If you talk about perhaps using it as an experiment to launch something at it and see how it responded, aren't you in a position of potentially causing a natural disaster to turn into a man-made
Right.
one? And so
Right.
how would you gather the data? Would you go to something like Apophis that has a pretty good probability of hitting Earth, or would you use that kind of experiment on something that is a definite zero probability of hitting Earth?
Yeah, it's a good question, and I certainly am being a bit flip. If it were not an object that had a real, although extremely small chance of hitting, then there's no problem. In other words, there are 1 million near-Earth asteroids that you could do this on. Doing it on Apophis could be problematic. Not that you're likely to cause a problem, but you don't want to get into that political issue at all. You don't want people taking you to court the month before launch saying, don't you dare do this because you're in danger of the Earth.
What happens if Apophis hits the ocean?
If Apophis hits the ocean, it's right near the borderline between a very big and ugly tsunami and perhaps not such a big one. If it in the close pass, let me rephrase that. If it should go through the keyhole and come back on April 13th of 2036, then we don't know whether it will hit, we don't know exactly where it will hit, but the line across the Earth that is basically the intersection of the Earth with the asteroid orbital plane. And part of that goes across the Pacific off Baja California. And maybe this helps justify why the gentleman from Orange County says he does not want to take the risk of an asteroid coming along and wiping out 1 million of his constituents. So the impact tsunami issue, as you well know, is very uncertain in this size range. At a 100-meter object, a Tunguska type object, it does not produce a wave, we're pretty sure. 1 kilometer object, we're pretty sure it would produce a wave. And this is somewhere in between. A wave, I mean, that would propagate for 1,000 kilometers.
2 quick questions. One is the difference between a rendezvous and a flyby deal with how fast you want to get the information? I mean, if you're trying to get there in a hurry, it inherently has to be a flyby. And the other is, there's talk about using a rendezvous as a space tractor to manipulate the orbit, and when that inherently, as talked about before, have a chance of altering the orbit.
Well, this is such a low-mass, low-cost spacecraft, it wouldn't produce much of a gravity tractor. If you want a gravity tractor, you need to send a few tons. The other, of course, people might argue for a flyby. I would say that the amount of the incremental information you get from a flyby is so small that I have a hard time imagining anybody doing it unless they just wanted the PR value of a picture. But I don't make those decisions.
How long will it take? I have 2 questions. How long will it take to find the remaining 20% of the large near-Earth asteroids, or a substantial portion of them? And the second question is, do we have any knowledge of whether any of the major impacts we know of in the past, or even minor impacts, were caused by comets? And what percentage of impacts on Earth have been comet rather than asteroid?
It's almost impossible to tell from the geological remnants of a large impact what it was that hit. In a small one, which is less energetic, you can find iron, for instance. In the size ranges we're talking about, the kilometer and larger, we're confident that comets only amount to 1% of the impact risk. In the sub-kilometer size, I have to say that no one has ever found a sub-kilometer comet at all. They may not exist. They may evaporate when they get that small. At the level of the KT extinction, no one knows. They might be more important relatively. Now, what was the first part?
The remaining 20%.
Yes, right. Well, it depends on what we do. If we just continue the current survey, then the fact is that they become less and less effective. We found the easy ones. We're onto this tail. When you first start the survey, everything you find is new. You get the low-hanging fruit. You get the asteroids that come by frequently. As the thing extends, it could take another decade to get that next 10%. But if you go to the larger telescope to conduct a deeper survey, then you more quickly pick those up. But we'll never get all the way. None of this is going to provide absolute surety. But it sure is a lot better than not doing anything. If someone, we all who sit near the San Andreas Fault, if someone can come along and tell you they could eliminate 50 or 90 or 99% of all the risk of earthquakes, boy, that would be really something. You wouldn't ask for 100%.
Dave, nice talk. I want to come back to the gravity tractor question. First of all, once you know the orbit, would a gravity tractor approach work for Apophis? And the second part of that is, how much do you really have to know about the mechanical, physical properties of Apophis if a gravity tractor is what you're going to do to change its orbit rather than trying to smash into it?
How many of you saw the show last night on, was it the History Channel? They're running an Armageddon week with all of these things. Ed Liu answered your question beautifully. The fact is, the gravity tractor is the only thing we know that does not depend in any way on the physical properties or spin or anything else of the object. All you have to know is, how close can you get before you bump into it. If you're really going to just use a gravity tractor, you eliminate most of the need for the kind of mission, predecessor mission.
You still need to know it's like an accurate orbit and not a precise one.
But I'm first answering his question about do you need to know the physical stuff to simply operate a gravity tractor. Now, the fact is, I don't think we are going to know whether we need one or not. If you actually knew where it was going with a precision of a kilometer or two, and you knew it was had a reasonable chance of going through that keyhole, and you simply wanted to deflect it a couple of kilometers, it's a simple thing to do with a gravity tractor. But how are you going to find out that precisely? I mean, it just is extremely difficult. And of course, Jack is absolutely correct. The Yarkovsky effect comes in, understanding solar radiation effects, understanding all those things. The fact is that if we improve the orbit, or even if you just improve the orbit with ground-based radar, the most likely thing is you will find it is not going through the keyhole. Only in that unlikely case that it's still, you know, when we reduce the uncertainty of the orbit from 1,000 kilometers to 10, and the keyhole is still within that 10 kilometers, then's when you start losing sleep at night, because it's very hard to get it more precise.
Yeah, I guess I'm still on the same topic. Early in the talk, you said that the asteroid knew whether it was going to hit the Earth because Newton's laws worked. Are there enough non-Newtonian forces with stochastic elements involved that maybe the asteroid doesn't know yet whether it's going to hit the Earth?
That's a very good question. And again, I was being a bit flip because I wasn't taking into account issues of going through a keyhole that's 600 meters wide. If you're talking about whether or not it'll hit a target the size of the Earth in any straightforward way, then of course all the even relativistic effects, Yarkovsky effects, non-Newtonian forces are small compared to that. If the question is will it go through a keyhole, it's very much harder. And maybe it is stochastic, and at the very least you probably have to track it for a long time in order to find out.
Thank you. Thinking of the cost of further surveys, I was wondering how close are you to the LSST people and to the possibility of doing parasitic research using that enormous telescope?
The LSST, the Large Synoptic Survey Telescope, is the ideal instrument for carrying out an advanced survey. Right now, we basically have a survey that can go down to 1 kilometer objects. Pan-STARRS, the Hawaii system, could take us down perhaps to 500 meter objects. LSST can take us down to 150 to 200 meters. And it can do so with very little impact on the rest of the observations. I think you all know LSST is going to be this incredible machine that covers the whole sky every week or so. It'll give you, Universe, the movie. There'll be this incredible flow of data. You can see everything that moves, everything that varies, everything that explodes. And near-Earth asteroids fall out of that not completely naturally because you have to have a certain cadence to get the data you want. And they have consistently put that forward as one of their primary objectives. And NASA has so far consistently been unwilling to give them any money because it's just NASA is a space agency. And one of the arguments we may actually have more success with instead of protecting the Earth is that a survey like that with the LSST is necessary to find near-Earth asteroid targets that are easy to reach by spacecraft that could be used for human spaceflight to near-Earth asteroids. But that's the subject of another talk.
Okay, last question.
So I want to, you mentioned several of these low order effects, maybe should say higher effects, that complicate the determination of the orbit, whether or not it's going to hit. Given that, my question really is, will this mission achieve its objective of determining the orbit accurately enough to answer this question? Or will there be even more unresolved questions that say, well, the Yarkovsky effect or something else is going, we need to observe it. We need another launch 6 years later to find that out.
I don't know. As I think I was indicating before, let me say it again. If, as you improve the knowledge of the orbit, you find that it will pass through the Earth plane in 2029 and not go through the keyhole, then you have solved the problem. And that's overwhelmingly the most likely thing. But it's possible, as you improve the orbit, that you'll find instead of moving away from the keyhole, it just converges down on it, in which case the mission is not good enough.